All right, FAQ Season 2, Episode 1, Tai-Danae. So happy to be here with you and excited to talk a little bit more in detail about a bunch of different aspects of quantum computing.
Yeah. Hey, Adam. Good to be here for Season 2.
Yeah, so I think a good way to maybe start this out, we're kind of like in the bubble. So I've been thinking about this a little bit lately. We're in this like very cutting edge, interesting company, SandboxAQ, and we're talking about quantum computing and quantum technology all the time. So I think for us, it's kind of a given that this is interesting.
Yeah.
We hope that if anybody's watching this conversation, they also think it's interesting. But like the funny thing is I was talking with my brother the other day about quantum computing and quantum technology, and like all of this stuff. And he asked me the question, like, why should I care? Like, why should I, my brother, care about quantum computing and quantum technology? And I realized that I didn't immediately have a really great answer for him. What do you think about that if somebody were to ask you that question?
Yeah, I don't know if I would have a great answer too. I'm kind of the perspective, well, you don't have to care. And that's totally fine. Sure. So that's kind of my first thought. But when your brother asked you that and you kind of thought of it for a while, did you come up with something on the spot or how did that go?
Yeah, I mean, a little bit. I don't know if it was like a really great answer that I came up with on the spot, but I've definitely been thinking about it. So, I mean, I agree with you that there's some kind of like innate curiosity, and like we're here for all curious humans on this particular podcast. So, I think that there's something there of just like this is a new way to think about nature and about how to use nature for computing and the context of quantum computing. So that's pretty cool, I think. Just like innately, the curiosity factor is pretty big, but also like there's a lot of potential. So I think there's a lot of potential in the field to do great things that could end up impacting virtually everybody. And I kind of like have a question at the end of that sentence because we don't really know yet. Like there aren't fully fault tolerant, huge quantum computers doing anything right now better than what you could do on a classical computer. Like in fact, it's quite the opposite. Like the classical computers are doing things in general much, much better, except for like some very specialized problems that don't really have any practical value out there. So I think that's a piece of it is this potential that quantum computing could have. And then tied up with that for me is kind of looking at past high-tech discoveries or high-tech innovations like artificial intelligence, for example, and seeing how there can be a real divide in folks that develop that technology and can use that technology and really have control over the development of that technology. And it creates this sort of technological gap or a divide between the haves and the have-nots, or the people that are developing the technology and then just the users of the technology. And we've run into this over and over again in technology and especially in computing in various ways in the past. And I think it would be great to try to avoid that with quantum computing. So I think that's another reason to care about it sort of in this early stage is the more people that are aware and caring about it, maybe we can try to minimize or even avoid a sort of quantum divide, like what we've seen with like bandwidth divides and AI divides and bias in AI and things like that. So those are some of the things that I maybe wish that I would have said when I was originally asked the question.
Yeah, nice. I want to say something on the like just pure curiosity side. When you get past all of the sophisticated mathematics and sort of hieroglyphic-y symbols of physics and math, and you think about the actual laws of nature that these engineers and scientists are harnessing to build this technology that you're speaking about, it's incredible. I mean, it's mind-blowing. And these are laws of nature that we take sort of take for granted every day. Like we just wake up, the sun rises, for like our entire lives. But when you actually start to dig a little bit deeper and realize what actually is being harnessed, which is kind of hard to do because not everyone is like super fluent in advanced mathematics or like, PhD in higher level physics. And I get that. But one thing that I am excited about, for this podcast and what we get to do is to try to take some of those ideas and like you were saying, help kind of bridge that gap. So even if you're you're not super interested in all of the nitty gritty about how the technology that you're using works, there is also just this delightful aspect that we live in an incredible world. And you never know, but one day after listening to, FAQ, you may just be walking down the sidewalk and remember something amazing. And, it's like, oh, that's awesome. Next time I think of how something in my computer works, I'm going to remember it's based on this incredible aspect of physics. And I just think, that kind of pure delight and wonder is also, a good reason to kind of think about these things.
And on the other side of it, like there are practicalities that are coming down the line. So the technology is advancing incredibly quickly. And even though we don't have those fault tolerant quantum computers yet, we probably will in the coming couple of years. And although we don't have like a great idea of a ton of different applications that might work on quantum computing to really sort of unlock amazing things in our world, one of the most exciting things for me with quantum computers is that, we only know a couple things that they could probably do well now. But once we actually have the technology, the functional technology in the hands of lots of people that are very creative, like who knows what the sort of killer application is going to end up being for use on quantum computers. Like we just don't know yet, but there's probably going to be some amazing things happening there. And for me, that's really exciting and hopefully inspiring to other people too.
Yeah, for sure. Looking forward into the future is good. Although it could lead to this pitfall that starts with an H and ends with the E and rhymes with pipe.
I think you might be talking about hype. Is that right?
Yeah, that's right. What do you think about the hype surrounding quantum computing?
Yeah, it's pretty thick.
Yeah.
I think it's some pretty thick hype, a very wide diameter pipe for a pipe.
Nice.
Something like that. Yeah. So I think that, I think one thing to think about is why is there so much hype? Because there is a ton of hype out there. From my perspective, one of the reasons why there's so much hype and it's so hard to kind of differentiate hype from reality is that we don't have quantum computers yet. So there's no sort of like foundational truth basis where somebody could make a claim and then you could look at the quantum computer and say like, no, that thing can't do that yet, or can't do that at all. Like right now they can't do anything really. So like there's no real basis. So there's just so much opportunity for people to be thinking in creative ways that it's very easy, a slippery slope to take those creative thoughts and just kind of extend them on into like, we could probably do something like this. And then that would allow us to do something like this. And then that would allow us to do something like this. And all of a sudden, like all of humanity's like woes are fixed by this technology. It's only a couple of steps to that. So I think that's part of the thing that's kind of driving the sort of hype. What do you think, Tai-Danae?
I think you're right. Something that's kind of funny when I ask people that I come across, are you familiar with quantum physics? Have you heard of quantum computers? Usually the answer I get is not, oh yeah, they're going to cure cancer, right? Or, oh yeah, they're going to solve world hunger, right? Actually, the answer that I usually get is, no, what's that? So I don't know what that means. It could just means I don't know a lot of people. But for those folks that are familiar, or at least have heard, in the news or whatever, maybe can you share some examples of things that are like definitely classified as hype, so that whoever's listening can have some examples. So when they go out and they're like, oh yeah, I remember that's not like for sure going to happen, but it's a possibility. Do you have some examples in mind?
Sure. Yeah. And actually, these examples come from people at SandboxAQ. So I actually asked this question in one of our one of our communication channels, talking with the actual physicists and other scientists and engineers in the company. And when I asked them, like, what are some examples of hype, I got a ton of things back. And I'll read through some of my notes here. Yeah. They kind of run the gambit. So some folks, one person said that a hypey thing that they often see, which I think is more of a miscommunication, and we can talk about this in future episodes, that quantum computers try every possible solution to a problem at the same time, and then you can easily just like pick out the right answer because you've done all of the, you've solved everything. You've gotten all of the possible solutions. And that's just a misunderstanding of how quantum computing works. A little bit more on the misunderstanding side than on the hype side. But one thing for the hype side that I got is that quantum computers will sort of magically solve the drug discovery problem. So the drug discovery problem has to do with electronic simulation. So simulating the interactions that molecules have with each other. And a drug, usually an effective drug will interact with another molecule, the target molecule, and do something, either make that target molecule less effective or more effective in the human body. And then that is basically how a drug works. So there's a lot of hype out there that quantum computers can simulate the electron movement and the way that the different molecules interact with each other like very, very well. And by doing that, you'll just magically solve everything that has to do with creating new drugs. And that's not really true. So there are elements of that are true. And I think that's where it gets really hard to sort of discern hype from reality. Quantum computers will absolutely help the drug discovery pipeline.
Or
those are some of the things that
you said the word will.
That's
Is
true.
It better to say
that's true.
May? Yeah.
I think especially when you say quantum computer. So thank you for keeping me on there.
Yeah.
Quantum inspired approaches are helping the drug discovery problem right now using classical hardware, but in a quantum inspired way. And that's maybe sounds a little hand wavy, and that's something that we can definitely talk more about later. But yeah, quantum computers are not doing that now, and they may be able to do that in the future. But right now, it's these quantum inspired algorithms and approaches on classical computers that are doing something. And in the future, quantum computers may be able to do that better, but they're still only as good as our understanding of the basic fundamentals of biology. So that's what I think this person was really trying to get at, is that that we need to understand the biological systems even better than we do now in order for quantum computers to even have a chance to really be able to unlock the full potential of this sort of molecular simulation. So it's a blanket statement of just quantum computers are going to like magically find new drugs and help all these different things is definitely hype. There's some nuggets of potential truth in there on the quantum computer side, and there's even more than nuggets of truth. There's some actual truth on that when you start thinking about quantum inspired approaches on classical hardware. Yeah. So it's a bit tricky there, but that was a good one.
Yeah. Okay. So the language of trying all things at the same time, drug discovery, what are some other examples of hype that you got?
So one person said anything that puts quantum and climate change into the same sentence is probably a good indicator that there's hype there. And again, there's like some nuggets of truth potentially there. I mean, clearly quantum computers aren't doing any of that work now. We've talked about that, but there's a lot of potential for quantum computers to be able to help discover and design new types of materials that maybe would be helpful for creating more efficient batteries or solar panels or other kinds of ways that could reduce our reliance on fossil fuel, or maybe even help with some of the carbon capture projects and things like that. So there's some potential there, but it's far from anything that's realized, and we don't 100% really even know what quantum computers might be able to do in that area. Really, and this came from another comment when I asked this question internally, like really the main thing that we are pretty sure, like I think the most sure that quantum computers can do has to do in the area of cybersecurity. And that's breaking the current security standards that we have on especially on the internet, but even outside of the internet, RSA encryption, for example, elliptical curve, cryptography. Those things are going to very likely be broken by a fault-tolerant large quantum computer. We know the algorithms like Shor's algorithm that will help us do that. And that's the one thing that we're like pretty sure is going to be a real thing. And anything on top of that likely involves a healthy dose of sort of speculation and assumptions. And depending on what you're talking about, it might be mostly speculation, or it might be, sort of data-informed, healthy speculation. It's just on that kind of spectrum.
Yeah. All right. All great points. So maybe now that we know some examples of hype that folks can, keep their eye out for, maybe we should just turn the conversation a little bit to like what actually is a quantum computer, because we haven't said that yet.
Before we get to that, Tai-Danae, if I can.
Yeah, go ahead.
I think one thing, and I'm actually going to share, and I know I didn't tell you I was going to do this, but I'm going to share my screen here. Oh. Okay, this is a one way to kind of frame all of this hype, and it can kind of be helpful by looking historically at other hypier things, especially in technology, and kind of establishing a framework for thinking about what might be happening with hype in quantum computing right now. So you can kind of see, like, the first thing when I first looked at this Gartner hype cycle is like, that is not a cycle. It doesn't seem like it actually comes around. So yeah, but I mean, I still think that it's important, even with that potential like odd flaw. Yeah, I don't totally understand the history of the word cycle in this, but you can see that like things start off with a technology trigger, and then you get this peak inflation of expectations, and then this trough of disillusionment, and then a slope of enlightenment and a plateau of productivity. So the alliteration is very strong in parts of this graphic, which is kind of nice. And I think where we are with quantum computers is close to that peak of inflated expectations. So we've had the technology trigger of like, we actually have quantum computers out there. They're functioning. They have, all sorts of error correction problems, and the bulk number of qubits is still low. And there's tons of engineering challenges that we still need to kind of get through to make them fully functional. But there's been a trigger of like, there are many quantum computers out there that are functional, and you can use them to do things. They just haven't unlocked their full potential. Once you get that trigger of like, oh, this thing is real, then all of a sudden, we get into these like assumptions and speculations about what they possibly could do. And I think that's where we're at right now, is that peak of inflated expectations. And if we kind of follow that along, what might happen is once we actually spend more time and build more fully functional quantum computers, or maybe it takes a long time to get there, we might go into this trough of disillusionment. That's happened with artificial intelligence several times over the past 50 years. And then now with AI, I think we're sort of somewhere between that slope of enlightenment and on the plateau of productivity when we see a lot of the applications of AI that have been coming out lately. So that's a way that I like to kind of think about this, looking at past technology like AI, and it makes a lot of sense to me when it comes to quantum computing. I don't know if you have any hot takes looking at this for the first time.
I have no hot takes, and I'm kind of bothered that it's labeled a cycle, but this is good. I'm glad that you brought this up. It's nice to know that people have thought deeply about this to even chart out where we are in the thick of things. So that's good. That was a good share. Thank you, Adam.
Oh, cool. Yeah, no, you're welcome. And I know that, we should actually talk about a little bit more detail about quantum computers and what we're going to do for this season 2 of the podcast. So
yes,
I'd love to hear your thoughts on that.
Okay. So you and I were chatting in the planning for this season about how best to go about this. And I like your decision. So let me kind of summarize it this way for the listeners. So I think we mentioned this even in one of our earlier episodes, maybe, but there are different ways that people can build a thing called a quantum computer. We mentioned also, I believe in episode 1 of season 1, that the kind of basis or the building blocks for such devices are called qubits. And these things have physical realizations like a photon or a bunch of photons or electrons, and et cetera, et cetera. So you and I had a choice in season 2. If we want to talk about quantum computers, do we talk about like all of the different things and all of the different components of all of the different flavors? And that would be a little bit overwhelming. So we decided we are going to pick one kind of quantum computer and slowly explain some facets that we think are interesting. And I want to actually say this for the benefit of listeners. Personally, when I have in the past attempted to learn about quantum computing stuff, generally I find that either the exposition or the video or the textbook starts kind of with like the theoretical math. A qubit is a vector in 2-dimensional Hilbert space, blah, blah, block sphere, blah, 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 blah. And then I'm like, okay, for me as a mathematician, I think, all right, I understand what they're saying. If I were not a mathematician, I would not understand what they're saying. But even as a mathematician, I still don't get what they're doing. Like, okay, you did all of this linear algebra stuff, but like, what's actually happening in the lab. Like what can I hold with my hands, quote unquote? Like what is really going on? I don't really want to know the theory. I actually want to know, what are you doing? And so I think that it would be helpful for us. I mean, we've talked about this before, to actually answer the question, like, how? Okay, qubit something, theory something, but like how? Or what? What's really going on? So to answer that question, we need to pick a kind of quantum computer, a specific platform, because there's a bunch of them. Like IBM has one, and Google has one, and Microsoft has one, and all these other startups have their own kind of thing. So we had to make a choice. Now, I think two of the most popular kinds of quantum computers deal with either these things called superconducting qubits or these things called trapped ions. Now, if for listeners, like, don't worry about what they are, but here's the thing. A trapped ion quantum computer is working directly with elements from nature. Like, you take an atom, you like kick off one of its electrons, and it has now a charge to it. And instead of calling it an atom, now you call it an ion, I-O-N. And then you're like dealing with the actual laws of nature. Okay, and you do cool stuff. On the other hand, the superconducting qubit, it's not like an atom. It's actually something that you build with your machines, and you're building a bunch of stuff to replicate or to duplicate the kind of laws that are already inherent in this thing in nature called an atom. And so if we're going to pick one of these two platforms, superconducting qubits kind of have an extra layer of pedagogical baggage, because you have to describe the nature that it's mimicking, but then you also have to describe like the stuff that the engineers made to mimic the laws of nature that were already hard to explain. And by laws of nature, I mean like the spin of an electron or things like that, or energy levels. So we decided, and I like this idea, that for the rest of season 2, we are going to pick trapped ion quantum computers and describe a little bit of the how, not just like theoretically, the math stuff and the ideas, and not even just like what are the potentials, as we just talked about, but actually what are people doing with these things? Okay, so that's kind of the game plan. But then there's another layer to that, like how do we do that? Where do we even begin? And I love your idea about going through this checklist called DiVincenzo's criteria. So maybe now I'll kind of hand it off to you. Do you want to say a few words about what this checklist is?
Sure. Yeah, I can give that a shot. And even before we get to that, I will say that yes, the idea of using trapped ions, I think, is a good thing for us to go through the trapped ions quantum computers. Most people, if they've heard anything about quantum computers, have probably heard about superconducting quantum computers. That's like what Google and some of these other folks that you mentioned, they're putting a lot of eggs in that basket, putting a lot of bets down. So we're going to do our best to make sure that anything that we talk about when it comes to trapped ions is transferable, like the basic understanding and basic knowledge should be relatively transferable to superconducting quantum computers. And we'll do our best to kind of throw a few sentences here and there to try to connect some of those dots. With the DiVincenzo, essentially it's a roadmap of telling you what you need to have, what type of criteria you need to be able to do a little check mark that like, yep, got that, in order for you to be able to say that you have a quantum computer that's actually functioning. And I think we're going to use those criteria and walk through them pretty much one-ish per episode starting next time, describing what those criteria are or what the specific one is. And then in the framework of a trapped ion quantum computer, saying how that particular physics setup satisfies that particular criteria in the list. So on the meta level, that's kind of how I think we're going to use it.
Yeah, no, that was perfect. I don't really want to add any more, but I will just say for context, these are 5 criteria that came out in a paper in the year 2000 from a researcher at IBM, David DiVincenzo. So these are a list of 5 things, and you can kind of think of it as like broken down into 3 categories. So the first 3, or depending on which order you write them, but 3 out of the 5 are describing something about qubits. Like you want to make sure that whatever qubits you use, they're like reasonable and you can work well. And they're like, these are like sensical things. The second sort of category has to do with what are called quantum gates. So that's just, and we'll talk about this later, but it's like, oh, you have these qubits and you're confident that they're going to work well. Okay. The next thing you want to make sure is that when you manipulate them, you have a way to do that. In practice, that's like shooting them with lasers or magnetic fields. We'll talk about that later. And then the last sort of category is like, okay, after you did all of that stuff, like what's the point, right? You should get something out of it that should inform you as to the problem that you're working with. And so that last criteria has to do with getting that readout or getting that answer. And so this is a checklist of 5 things that are very reasonable, and it's kind of paving the way for engineers and saying, okay, now that you know about the world of quantum physics, here's actually some reasonable things you want to keep in your mind as you go into the lab and as you start engineering these things. And did you check off all 5 things? Then you're good to go. It looks like you've got a good quantum computer. So I like you're keeping it meta, and I like to think of it as kind of being divided into 3 groups, and then we'll just take it from there and see how things go.
I like that. So yeah, next time we're going to start to tackle the first criteria that we're going to work with. So that'll be sort of our first foray into this more detailed description of really functionally, how does a quantum computer actually work and what does that mean? So we're going beyond the theory, and hopefully by the end of this, you're going to be able to like have a couple of clicks, maybe 2 clicks deeper into understanding like physically what is happening inside some of these like very cool looking quantum computers that you may see online or in news articles. And along the way, hopefully we'll hit some more of those like hype versus reality types of things.
Yeah.
So,
this is going to be so good.
Yeah.
I'm excited.
I know. I'm looking forward to it. Great. Well, can't wait to continue the conversation in a couple of weeks, Tai-Danae.
Yeah, me too. See y'all next time.